Hello, I'm Ed Powley from Falmouth University. Today I'm going to be talking about some work that I did in collaboration with my colleagues at the University of York and at AI Factory Limited. In particular, we're looking at one of AI Factory's products. This is a version of the popular card game Spades, which runs on Android mobile phones and tablets. To date, this has been downloaded around 6.5 million times from the Google Play Store, so it's one of AI Factory's most popular and successful products. In previous work, we looked at creating stronger AI players for Spades, in particular using an algorithm known as Monte Carlo tree search. MCTS works by building up a playout policy, which initially starts out random, just choosing legal moves completely at random, but gradually converges towards actually playing intelligently based on the results of the earlier, more random playouts. So we implemented MCTS in AI Factory Spades and tested it against the existing AI in the product, which was mostly based on hand-coded heuristics. And as you can see here, our MCTS player wins around 65% of games against the existing AI. This is a great result. However, despite the AI player having a strong win rate, it still sometimes appears to do things that humans perceive as not really being sensible plays. So when MCTS was first integrated into AI Factory Spades, they received a number of reports from beta testers highlighting particular weak plays that the AI player sometimes makes. Now, it sometimes turns out that the play that the AI made, which is perceived as not being particularly intelligent, actually is fine, or at the very least is not as bad as the human tester perceived it to be. However, human perception is obviously important in terms of how strong or weak the AI is perceived to be, so this is still worth fixing. And the solution that we previously had was to add heuristics and knowledge into the search so that in this type of situation, the search would be steered away from the weak-looking play and towards the kind of play that an expert spades player might expect the AI to make. Now, the interesting thing about this is if you look at the actual playing strength in terms of win rate, these pieces of knowledge and heuristics actually don't affect the win rate at all. However, looking at the perception of the players and looking at the reports that come in from the players, there is a measurable difference in how clever the AI is perceived to be. So addition of heuristic knowledge is a good solution to this problem. However, it does require a high degree of human expertise, both in the specific game, in knowledge of expert level spades strategies, and also in terms of more general, in terms of designing heuristics for this type of search-based AI. So the question we asked in this work is, can we automate this somehow, and can we use machine learning in particular to reduce this burden of human expertise in fixing these perceived bad plays? Now, it's important to emphasize what our goal is here with this work. We're trying to make the AI, in a sense, more human-like. We're trying to improve the perception of the AI as an agent that is intelligent in the same way that a human player of spades would be intelligent. What we are not trying to do is make the AI objectively stronger in terms of win rate. And this is the main difference between the work I'm describing now and something like AlphaGo, where obviously the ultimate aim of the project was to create an AI player that could beat the human world champion. So we collected some data from the players of AI Factory Spades. We took a sample of 690 unique player IDs. Between them, they played nearly 28,000 full games of spades. And in terms of individual plays, just by the human player, just over 1.33 million. So each of these specifying the state of the game and the card that the human player chose to play in that situation. So we collected this data and pulled it into TensorFlow and started to look at what traits of human play we could learn from the data and how we could use that to make the MCTS-based AI player in some sense more human-like. So we make a distinction here between direct imitation and indirect imitation. So we look first at direct imitation, which is just training a neural network to imitate human players, in the sense of if you give the neural network the same game state, it will return the same move that a human player would make when presented with that state. So our input to the network, consisting of the cards in the player's hand, followed by the cards that have been played this trick. And then in spades, each round starts with a bidding phase where players try to predict how many tricks they're going to take. So we also pass into the network information on the bids that each player made and how many tricks they've won so far in this round. This then gets fed into the network. We tried various different network architectures here. And in each case, the output of the network specifies which card to play in the game. Or at least that's the format of the training data. When we actually run the network that's been trained, what we get is a probability distribution. In our case, we just look at whichever entry in that distribution has the maximal value and take that as the card to play. So we trained this network using our training data, keeping some of that data back as a test set, and then evaluated the accuracy of the network on that test set. Accuracy here meaning the proportion of items in the test set where the card chosen by the human player is the same as the card chosen by the network. We also looked at using these networks as an AI player and measured the win rate of these players against the MCTS-based player used in AI Factory Spades. We experimented with several different network architectures in terms of number and size of layers, whether or not we actually connect the tricks bid and tricks won inputs of the network, and whether we use convolutional layers, and if we do, how we combine the outputs of those layers with the rest of the inputs. And we compared all of these against the baseline ISMCTS player present in AI Factory Spades and a random AI player which just selects a random legal move from each game state. So in terms of accuracy, we found that basically all of the network architectures we tried achieved an accuracy around 70%. This is compared to MCTS with heuristic knowledge, which achieves 58.2%. Interesting to note here that even the random player achieves an accuracy of 44%. The reason for this is in spades there are a lot of situations where there's only one legal move, so you have no choice but to agree with the human player, or cases where there's, say, two legal moves, so you have a 50-50 chance of agreeing with a human player. If we look at win rate, it varies a little bit between network architectures, but none of them are achieving more than 20-22% win rate against a basic MCTS player. our network architecture isn't restricted to choosing legal moves. It just outputs a probability distribution over all cards. So it can assign a non-zero value to a card which isn't legal to be played in that situation, or even a card that the player doesn't actually hold. However, we found that in the vast majority of cases, 99.95%, the move that is ranked highest by the network is actually a legal move. So without explicitly being trained to do so, the network has, in some sense, learnt what constitutes a legal move in spades, which is not a trivial thing to learn. So we've seen that direct imitation gives us good accuracy, but pretty poor performance in terms of playing strength. We now look at indirect imitation to try and address this. So instead of using the network directly as an AI agent, instead using that network within the MCTS agent to try and steer it towards these human-like plays. So there are many different ways to integrate neural networks with MCTS. AlphaGo famously uses 2 or 3 different ways, but we are particularly looking at modifying the selection phase of the MCTS algorithm. Selection in MCTS often uses the UCT formula. Basically, you calculate this quantity for each of the branches you can take at a particular point in the tree and go down the branch that gives you the maximum value. We use a technique known as knowledge bias, in which you add a third term to the UCT formula, and this term is proportional to the value that your neural network assigns to the move in question. So the higher that value, the more likely you are to choose that move. And there's a couple of parameters to tune here, and this term in the equation is set up so that the influence of the network decays over time. So basically the network values give MCTS an initial steer towards certain areas of the tree, but then later on the MCTS algorithm takes over and can overrule that initial steer if it determines that it's beneficial to do so. Now, we experimented with a few different ways of using this in MCTS, because one of the big problems with this is it can be expensive to invoke your network to evaluate the moves from a particular node. And somewhat surprisingly, we actually found that we can get a pretty decent level of performance by just limiting this modified selection to the root node of the tree. So at deeper levels in the tree, we don't use the network at all. We just use it for that first step in selection. And that actually means that we only need to invoke the network once. We invoke it at the root node, we store the values it returns, and for the rest of this instance of MCTS, we don't need to invoke the network again. So it's very cheap computationally, and the results it gives are pretty much as good as the results we were seeing from invoking the network more often at more places in the tree. So I mentioned we've got these 2 parameters in the knowledge bias term that we can tune. These essentially let us trade off between win rate and accuracy. If we increase the accuracy of our player, either by increasing the CBT parameter or by increasing the K parameter, then there's a corresponding decrease in the win rate that we see from the player overall. For our experiments, we chose CBT equals 0.2 and K equals 1000, because that gives a reasonable trade-off between the two. With these parameter values, we see a win rate of around 45% and an accuracy of just over 70%. So if we compare the results of direct and indirect imitation, in terms of accuracy, we can see that this indirect imitation using the network in a knowledge bias fashion within MCTS, achieves very similar accuracy scores to direct imitation. So the accuracy of the augmented MCTS player is at a similar level to the accuracy of the network itself. However, the real benefit, of course, of using MCTS rather than using the networks directly is in terms of win rate. So we're seeing win rates of 45 to 50%, so only a little worse than our MCTS baseline player. So without having too much impact on playing strength, we've vastly improved the accuracy of the player in terms of agreement with moves that humans play. Future work is to test whether this genuinely does lead to improved perception of how smart the AI is. But our hypothesis is that improving the accuracy will improve the perception of the AI's intelligence. So to sum up, we've shown that machine learning can be used to improve the accuracy in terms of agreement with what humans would do of an MCTS player, and we argue that that can be seen as an improvement in the human-likeness of the MCTS player. And once the networks have been trained, which takes a few hours in our cases, there's very little computational cost to modifying MCTS in this way. And by tweaking the parameters, you can trade off between accuracy and playing strength. It's interesting that we've seen this trade-off in the sense of, to increase the accuracy beyond a certain level, you necessarily have to sacrifice some playing strength. It'll be interesting to see if that's a property of spades and games like it, or if that's a more general principle that to be perceived as more human-like, you have to give up something in terms of play strength. That concludes this talk. Thank you very much for watching.